Last month, a car-sized rock exploded above Germany without formal warning. It was caught by lightning satellites, not by asteroid surveys. The immediate takeaway is simple. Small space rocks give almost no warning. They are tiny, dark, fast, and easy to miss. Earth's air then lights them up and sometimes blows them apart. So why are the bright explosions feeling more common right now? Start with a sky so clear you can count Orion's stars. Then a white streak slices across, brighter than Venus at dusk. A fireball means a meteor brighter than magnitude -4. That's bright enough to cast shadows and grab every nearby camera. We notice more now because our eyes and sensors multiplied. Doorbells watch the sky, while dashcams roll through every commute. Networks of all sky cameras stitch alerts across entire countries. Lightning mappers in orbit flag sudden flashes over dark oceans. One sentence recap: more watchers means more reported fireballs, not always more rocks. Here's the catch that fuels anxiety: some arrive with zero notice. Most meteor-class meteoroids are dim until they hit thick air. They reflect little sunlight and fall from awkward sunward directions. Surveys chase bigger threats, so tiny ones slip through gaps. Atmospheric entry does the amplifying, turning dim stones into daylight. Frictional heating ablates the surface and releases glowing vapor. Pressure rips the object apart and spreads fragments like buckshot. The flash looks huge, yet the rock might weigh a ton. That's a compact car's mass, moving faster than a rifle bullet. A real case helps. 2024 B-Zone was spotted hours ahead. It flared above Germany before dawn and fizzled safely as fire. Bottom line, more cameras and satellites make ordinary events feel extraordinary. Picture a stone diving into thicker air, layer by layer. An airburst is an explosion caused by rapid atmospheric breakup. The risk comes from shockwaves, not from pieces hitting people. Ram pressure builds as speed stays hypersonic, while density climbs. When pressure exceeds the rock's strength, fragmentation happens in milliseconds. Each fragment sees more air, and the breakup cascades violently. Material ablates into plasma, which radiates as a blinding fireball. Only a few % of kinetic energy becomes visible light. The rest drives shock fronts that race outward like ripples. Rule of thumb: altitude sets damage, not just the total energy. Chelyabinsk shows the script with painful clarity and reliable numbers. A 20-meter asteroid entered at about 19 kilometers per second. It ruptured near 30 kilometers up, releasing hundreds of kilotons. Windows blew inward across a wide region, injuring over 1,000. The object never reached the ground intact, yet the wave hurt. Smaller meter-class objects release far less, usually sub-kiloton energies. They burst higher and fade before the wave can break windows. Even so, a sonic boom can rattle nerves and set car alarms. Example: in real terms, a 1-meter rock might flash like lightning. It will confuse people for seconds, then vanish as smoke wisps. So the picture is, air makes small rocks loud, then harmless. Now shift from sky drama to the tools quietly counting flashes. A global patchwork tracks these events with overlapping sensing modalities. All sky camera networks report coordinates, brightness, and flight direction overnight. Geostationary lightning mappers register brief optical bursts above thick clouds. Military and weather satellites also see thermal flickers over open water. Infrasound arrays hear pressure waves and triangulate burst locations precisely. Seismometers can tick from distant booms, confirming timing and energy. Data then funnels into catalogs like NASA's public Bolide list. These feeds mean a mundane truth: detection has outpaced the phenomena. We are not summoning more rocks, we're just catching more flashes. Quick example: Atlas can spot small impactors only hours ahead. It flagged 2022 EB5 before splashdown near Iceland's wind-torn seas. Follow-ups measured the entry path and refined the estimated size. Social video finishes the mosaic, giving frame-by-frame flight reconstructions. Citizen footage now stitches with satellite timestamps for accuracy. Rule of thumb: 3 sensors make a story you can trust. With that redundancy, false alarms shrink and confidence rises sharply. Result: the internet fills with verified fireballs almost every week. That visibility feels like a surge, even if rates stayed steady. Net result: better ears and eyes create the sense of a spike. Here's the sneaky part that frustrates asteroid hunters every summer morning. The Sunward blind spot hides small objects racing in from daylight. Telescopes avoid bright skies because scattered light drowns faint targets. Even infrared systems struggle when background heat swamps a weak signal. Small impactors are dark, rotating, and often low contrast against haze. Approach geometry then shortens warning from months to mere hours. Many are only visible once the sky turns blue above. By then they are already inside the final approach corridor. A concrete case proves it. 2019 MO was seen hours early. It approached from a tough angle, then popped over the Caribbean. Discoverers posted coordinates, and satellites confirmed the predicted airburst glow. Similar constraints plague many events logged on NASA's Bolide site. We also misclassify spacecraft re-entries, which complicates early warnings occasionally. Data fusion helps clean that up, but constraints still bite. Astronomers call the key angle solar elongation, measured from the sun. Warning improves once an object reaches safe elongations after midnight. Twilight surveys push hard there, but coverage gaps still remain. Even radar can't help until targets are already very close. So the blind spot persists, and tiny rocks stay mostly invisible. Bottom line, geometry and glare explain many of the surprise arrivals. Some nights feel busier because Earth is plowing through debris. Meteoroid streams are dusty trails shed by comets and asteroids. They wrap the sun like braided ribbons across the inner system. When our orbit crosses a ribbon, meteor activity climbs for weeks. That includes slow, brilliant fireballs with lazy sparks and glowing trains. The Taurid complex is famous for that dramatic, low-speed display. It likely includes many chunky fragments, not just sand grain dust. Encounters vary yearly as Jupiter tugs the stream into swarms. In some years, observers report unusual numbers of bright, slow bolides. Reports spiked in 2015, then again in several recent autumns. Geminids delivered December fireworks too, but with faster, harder hits. They come from an asteroid-like parent 320 Phaethon, not a comet. Different parent bodies mean different speeds, colors, and fragmentation styles. Example in real terms, Taurid fireballs often drift across half the sky. A single event can last 5 seconds while lighting the landscape. Doorbell cameras love those, and social feeds saturate with orange streaks. That visibility makes a normal shower feel like a sudden outbreak. Bottom line, calendar streams bunch bright events and amplify perception. Let's ground this in named impacts you can look up tonight. A predicted impact is a small meteoroid detected before entry. Chelyabinsk in 2013 is the benchmark, despite being much larger. It was roughly 20 meters wide and released huge energy. Over 1,000 people were hurt by shattered window glass. Fragments fell on snow, and divers recovered pieces from a lake. That damage scares people, but it is a rare scale. Smaller, meter-class cases show the common pattern we see. 2008 TC3 was discovered a day before Sudan's pre-dawn airburst. Observers photographed entry, and researchers collected hundreds of meteorites at dawn. 2018 LA arrived over Botswana, with pieces later recovered on planes. 2019 MO lit up the Caribbean skies after pre-impact detection. 2022 EB5 was predicted hours ahead, then flared near Iceland. 2023 C-Zone crossed France and the Channel after midnight predictions. 2024 B-Zone was spotted before dawn and burned above Berlin. Each was car-sized, fast, and safely exploded high in air. The energy was loud, but the effects stayed purely sensational. Quick recap, fewer than 10 have been predicted before entry so far. That small number reflects difficulty, not a lack of effort. As pipelines improve, more of these tiny guys will be tagged. Net result, case histories match the pattern, bright, but mostly harmless arrivals. Why are there so many small pieces in near-Earth space lately? Sunlight itself can spin rubble pile asteroids faster over long times. The YORP effect describes that torque from uneven thermal radiation. Once spin exceeds cohesion, pebbles and boulders drift off gently. Close planetary passes can shake them too, loosening weak surfaces. Micrometeoroid hits and heat cycles also crack rocks into shards. These processes refill the small body population without major collisions required. Fresh fragments fall into Earth-crossing paths through subtle gravitational nudges. Jupiter stirs resonances that pump eccentricity and change orbital timing. Thermal forces tweak semi-major axes, inching fragments toward intersection points. Example in real terms, Phaethon's repeated heating likely birthed the Geminids. Asteroid 2003 Ehone is linked with the Quadrantids as well. Even comets can split, leaving knuckles of denser chunks behind. Those chunks shine as fireballs when Earth slices through the trail. Rule of thumb, more fragmentation means many small hits and fewer big ones. That distribution bias makes noise online, without raising real danger dramatically. Surveys confirm many asteroids are loose aggregates, not solid monoliths. That structure promotes shedding, especially after gentle tidal flexing. Net result, the conveyor belt of pebbles stays on. One sentence recap: slow physics feeds the supply of tiny impactors steadily. What would true early warning look like for these tiny intruders? Early warning means detection hours to days before entry. Infrared eyes in space change the game by seeing warmed rocks. NASA's NEO Surveyor aims to map dark objects against cold space. From space, it avoids weather, twilight glare, and most bright backgrounds. It targets hazardous sizes, but also catches incidental smaller companions. Ground support adds coverage with fast scanning telescopes across both hemispheres. Atlas patrols all-night skies, looking for motion against the stars. Pan-STARRS and Catalina provide deeper reach, with precise follow-up astrometry. Europe's Fly concept splits views, to scan wide patches quickly. Vera Rubin Observatory will discover countless faint objects during nightly surveys. Day-side gaps get help from heliophysics imagers near the sun. Specialized telescopes at dawn and dusk watch low elongations aggressively. Overhead, lightning mappers keep flagging sudden flashes in real time. Infrasound confirms bursts within minutes, closing the verification loop. Combine those feeds and timeline warnings stretch from seconds to hours. Example in real terms, recent impacts were predicted 2 to 7 hours. With more cadence, many could be tagged a day before entry. Glide paths would be posted and communities could expect the boom. Rule of thumb, infrared space surveys plus rapid cadence shift the odds. Bottom line, warnings will grow, but tiny objects will still surprise. So that Berlin-style flash felt sudden because it truly was. Small, dark rocks hide well until air turns them spectacular. Better sensors make them famous, not more frequent or more dangerous. If this helped decode those midnight booms, share it with a friend. Thanks for hanging out under the sky. See you next time.